there's an application of matrices that's related to probability, and it's called transition matrices. And I'll use as sort of an instructive example. There's a town, and in the town there's two barbers that cut hair. There's what we'll call the good barber, so he is talented, gives you a good haircut, and there is the bad barber. Now, to measure sort of how good these barbers are, after someone gets a haircut there, if they go to the good barber, it's more likely they're going to go to the good barber the next time. And if they go to the bad barber, it's less likely they're going to go to the bad barber the next time. So let's sort of quantify this. If you go to the good barber, there's a 75% that you'll go next time also. And that makes it a 25% chance that you switch next time. Now the bad barber's pretty bad. There's only a 5% chance that if you go to the bad barber, you will sort of stay with the bad barber for your next haircut. And 95% of the people, that implies that 95% of the people that go to the bad barber 1 month will go to the good barber next month. But the people in this town don't have great memories. So you might go to the bad barber, switch to the good barber, and then still 25% of those people are going to end up switching back to the bad barber because they don't think, oh, I went to this bad barber 2 months ago. They only think really 1 month at a time. So let's see what happens with a specific scenario. So let's say there's 100 people in the town, and these two barbers both open up at the same time, so no one knows which one's good and which one's bad. And let's say that 50 go to the good barber, and the other 50 go to the bad barber. So what's going to happen the next month? Well, the next month, I'll say good, bad. It's not going to be 50-50 anymore. It's going to be more to the good barber. But to calculate that out, I can take 75%, or 75% of the 50 people are going to go to the good barber. Those are these people. 75% of them, whereas 25% of them, of those 50, are going to go to the bad barber next time. But you're also going to get the people that switched. So he's going to get 95% of the 50 people that went to the bad barber are going to switch to him, whereas only 5% of the people that went to the bad barber will stay with that bad barber. Now, if you calculate this out, you end up with 85 people that go to the good barber, and only 15 go to the bad barber. Now, this can be modeled with matrices, because you notice we have like something times something plus something times something, and something times something plus something times something. Well, that's what happens when we do matrix multiplication. So one way that I can model this is take the number of people that went to the good and the bad and multiply it by this transition matrix. And what this is, I'll say good, bad, good, bad. So I get these numbers in the right order. So this 0.95 means if I go to the bad barber, there's a 95% chance that I'll go to the good barber next time. And this 75 means if I go to the good barber, there's a 75% chance I go to the good barber next time. But look what happens when I do this multiplication. I'm going to get a 2 by 1 matrix. And when I do the calculation here, I end up multiplying these two numbers by these two numbers, and I end up with 0.75 times 50 plus 0.95 times 50, which is exactly what happens over here. And we get the answer, which is 85 and 15. Now, if I want to know what happens 2 months from now, keep in mind it's not going to just go down to 0 for the good barber, for the bad barber, because some people are going to switch back. So if I do the multiplication again, 0.75, 0.25, 0.95, 0.05, I could go like this. And I would end up the next month with 78 compared to 22. Because there was so many people going to the good barber that the 25% that switched was actually a lot, and it kind of overcame the other amount. So it ends up being a little more for that second month. And you'd find that the numbers would kind of jump around. This could also be done if you have a calculator in one step, by doing to the second power and then multiplying it by the initial, we call it the initial state. That would also get me to this 78.22. Now you might want to know if this thing hits some kind of equilibrium. Well, if you were to change this exponent to something really high, like 100, these numbers would actually become, they wouldn't change by that much. It would be 79 and 21. And that would actually be like an equilibrium, because then the number of people switching. So when it's 79-21, the people switching from one to the other balances out. Now you might want to know, is there some sort of way to calculate out this equilibrium? And let me show you how you could calculate that out. So you say 0.75. So I take that matrix with the information, 0.95, 0.05. And if there's 100 people, I'm going to call this x and this 100 minus x. And I want to figure out what x is, so we'd be in this equilibrium. So if that happened, the answer after multiplying would continue to be x times 100 minus x. Now, you could take, we could do this pretty easily actually. If I take this row and this column and multiply them together the way we do with multiplying matrices, we get 0.75x plus 0.95 times 100 minus x is equal to x. You could, if you wanted to, use this, this, and that also, but you don't need to, because now I get 0.75x plus 95 minus 0.95x is equal to x. This ends up being 1.2x equals 95. And x becomes 79, and 1, 6. So that's the equilibrium point, 79. You know, you can't have 1, 6 of a person. I suppose you could have him cut a portion of your hair and have the other person do the rest. But basically that's the 79, 21 equilibrium. Now before I go to another scenario, I want to show you that in what we've just done, we had a sort of starting condition, an initial state, like it starts off as 50 and 50. But even without those numbers, if you take this so-called transition matrix, 0.95, 0.25, 0.05, and take that just as it is and square it, it becomes this matrix. And this matrix basically says good, bad, good, bad. These are the four numbers that say that if I go to the good barber, this 0.8 means there's an 80% chance that I'll be at the good barber again 2 haircuts from now. And a 20% chance I'll be with the bad barber exactly 2 haircuts from now. So squaring one of those transition matrices on its own gives us another transition matrix, which gives us information about, just what happens 2 cycles from now. Here's another scenario. It's kind of a contrived situation, but I have this number line, and I have 1, 2, and 3, sort of 3 points on it. And there's this particle, let's say, and it can only end up in position 1, 2, or 3, and every time interval it may or may not move. So here's the situation. If you're here on position 2, there's a 1/3 chance that you'll move to position 3, a 1/3 chance you'll move to position 1, and a 1/3 chance that you won't move at all. If you're on position 1, since you can only go to a place that's next to you, so you basically have a 50-50 chance that you'll either move to position 2 or you'll stay at position 1. And for position 3, there's a 50% chance that you'll move to 2 and a 50% chance that you'll stay where you are. So you can only move in one spot. So if I wanted to model this with a transition matrix, the columns are going to be like where I am now, and this is where I'm going to move to. So if I'm at 1, there's a 50% chance I'll stay at 1, a 50% chance I'll move to 2, and no chance that I'll go to 3. If I'm at 2, there's a 1/3 chance of staying or moving left or right. And if I'm in position 3, there's no chance I'll get to 1, but there's a 50-50 chance that I'll either stay where I am or move. Now if I take this matrix and I raise it to a power, well, there's a couple of things I can do now. I can say something like, if I'm currently at position 3, where will I be 5 places from now? The way I would model that is by using these numbers here. Could be percents in the state that I'm in. So this would mean I am in position 3, 100% chance that I am, and I'm not here or here. And if I raise this to the 5th power, that would tell me the chances that if I'm on position 3 right now, where I will be, 5 times from now. Or we could actually get even more information now by just raising it to a power. For instance, let's just say I raise it to the 2nd power. When I raise this matrix to the 2nd power, it turns into a 3x3 matrix, which is 5 12, 5 12ths, 1 6, 5 18ths, 4 9ths, 5 18ths, 1 6, 5/12, 5/12. And these 9 numbers tell me, if any of these 9 numbers, like this one here, says that if I'm in position 2, there's a 5/18 chance I'll be in position 1 2 moves from now. And here's one more scenario. We have 2 gamblers, A and B. A starts with $3 and B starts with $2. And they play a game where A has a 3/4 chance at winning and B only has a 1/4 chance at winning. So A's better than B. And they're going to just keep playing the game over and over. And the question is, what's the probability that A has $5 after exactly 4 games? So here's what the transition matrix looks like for this one. Now, once you have $5, the other person's out of money, and the game just does not continue. So it looks like this. Here I'm tracking A's money. So this is A, this is A sort of before the next game, and this is A after. Now the reason I have a 1 here is if A has no dollars, the game's over, so there's a 100% chance that he will have no money the next time also, because the game ends. But if he has $1, there's a 1/4 of a chance that he ends up at 0, and there's a 3/4 chance he ends up at 2. But see how there's a 0 here? There's no chance. His score has to change each time. So he ends up with this transition matrix. And if I take that thing, and in this case they're asking after 4 flips or after 4 games, what happens? So I would raise this thing to the 4th power, and then I would see what number. The question was, what's the probability that? What was the question here? That he'll have $5 after 4 games. So you raise it to the 4th power. He's starting with 3, so I want to track that number over there. And I popped it into the calculator, and all kinds of different numbers come out, but this number turns into 99 over 128. So that would mean there's about a 77% chance that he'll win after 4 times. Now, he might win sooner or he might win later, but the chance that exactly 4 games from now he will have achieved the 5 wins is a 77% chance.